This is a lecture on properties of ionic compounds, addressing target 4.4, describing the properties of ionic substances, including what happens when salt dissolves in water to form a solution, why ionic substances conduct electricity, and why they are brittle. The general appearance at room temperature of ionic substances is a crystalline or a crystal structure, orderly arrangement of ions. They are solid at room temperature, and they occur in a variety of colors. Some common ones are even white, like sodium chloride, salt. Other examples include CaF2, commonly known as fluorite, or Fe2O3, otherwise known as hematite. Notice the chemical name includes, the chemical formula includes the metal first, followed by the anion, which is the nonmetal. Also in this ionic compound, the metal, calcium, which acts as the cation, followed by the fluoride, which is the anion, negatively charged. Do they have high or low melting points? Large attractive forces in ionic compounds result in a stable overall structure. The stability is reflected in NaCl, sodium chloride, in its high melting point of about 800 degrees Celsius. Ionic compounds generally have high melting points. Here's a look at sodium chloride's atomic structure. Notice that the green spheres are anions, the chloride ions negatively charged, and the purple spheres are sodium ions, cations positively charged. And they are arranged in an orderly fashion with charges alternating. So we have a negative, positive, negative, positive, negative, positive, and so on. We call this a crystalline or crystal structure. Do ionic compounds conduct electricity when dissolved in water? Ionic compounds can conduct an electric current when dissolved in water. When a voltage is applied, the orderly crystal structure breaks down. In our lab, ionic compounds and properties, we applied a voltage using the battery, which was in our conductivity meters. Once dissolved, the ions are free to move about in the solution. The cations migrate freely to the negative electrode, and the anions migrate freely to the positive electrode. Here's a picture of sodium chloride melted down or dissolved in water and attached to a power source, which provides the voltage. Once dissolved or melted, the sodium and chloride ions will dissolve in the liquid. Once dissolved, they are said to be in solution. And in this ionic solution, sodium chloride is not a compound anymore. It has dissociated into ions. The purple ions are now free to move, and they are attracted to the negative electrode, as shown here. The green chloride ions are attracted to the positive electrode, as shown here. So they're free to move in solution once dissolved. Here's an animation that will show how water dissolves ionic compounds.
Forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
And when it does, the result is a hydration shell around each of the ions, peeling each ion away from the crystal structure and getting dissolved in the water. So as you see here, the positive sodium ion is surrounded by water. We call this a hydration shell. This shell is formed around each of the ions. The difference is water is a polar molecule, and the negatively charged end of the molecule is attracted to the sodium molecules or the sodium ions, while the positively charged end of the water molecule is attracted to the chloride ions. And they dissociate. This hydration shell prevents the sodium ions and the chloride ions from forming ionic bonds. So it's no longer a compound or an ionic substance. It's dissociated in water. Are ionic compounds malleable? No, they're not. They're brittle. And why is that? Well, they're brittle because they easily break apart. The crystal or the crystalline solids of structure of these ionic compounds alternate positive and negative ions, as shown here. Positive, negative, and so on in a very organized structure. When applied with force, in our lab, there was a hammer available. And when pounded with a hammer, the force of the hammer pushes the ions so that the like-charged ions are next to each other. Here's an example of like-charged ions next to each other. 2 positive next to each other, 2 negative next to each other, 2 positive, and so on. As opposed to before the force was applied with the hammer, where we still had the alternating positive and negative ions, causing that attraction because opposite charges attract. But now, once applied with force by a hammer, these positive charges and negative charges are now lined up with one another. And because like charges are lined up with one another, they repel. Like charges repel. And they are brittle because they break apart. So these ionic compounds are not malleable. They are brittle. They will break apart when an applied force from a hammer is used. And the solid breaking apart is represented here in this illustration. So a recap on properties of ionic compounds. What happens when salt dissolves in water to form a solution? Well, water forms a hydration shell around the ions. This prevents the ionic bond from forming. Why do ionic substances or salts conduct electricity? Well, once ions dissolve in the water, they are freely moving. Cations attracted to the negative electrode, the anions are attracted to the positive electrode. And why are they brittle? When the orderly arrangement is disrupted by a hammer, for example, the like charges line up and repel. The repulsion is what breaks the compound apart.